started doing a little differently at the request of a student, and hopefully you noticed this. When you go into the online presentation material, I'm now putting a timestamp on it so you know how long it is, so that whenever somebody looks in one of these folders, they know what that means. On the first one, I'm putting a little note there that says that the time given in parentheses is in minutes and seconds, and it's a summation of all of the voiceovers. When I do the recording of the voiceovers, I have a program that, you know, capturing the voice data, and then it tells me how long that track is. And then I attach that into the presentation software. So I just write down all of those timestamps for each of the voiceovers, and I add them up, and I get that. So it says there that it, what does it say? Does not include the time for each transition. So it takes some fraction of a second for the presentation software to move from one slide or screen view to the next. Okay, so it might not be an exact number of how long that presentation is. Whenever the timestamp ends up at a fraction of a second, like if it's a 32.5 seconds thing, I always round it up. Okay, if it's 32.1 seconds, I round it up. So hopefully that rounding up of all of the voiceovers will account for the time it takes for the program to move from screen view to screen view. So these might be pretty accurate representations. But one of the students in one of my other classes was saying she'd appreciate knowing how long each one is, because she had sat down to watch something and she had to go to work, and she wasn't sure if she'd have time to finish it before she had to get up and walk away. And she'd, of course, be so enthralled by listening to my melodious voice that she'd have forgotten to stop and go to work. So I've put them in there. It is kind of interesting because it is telling me a little bit about how bad I am at trying to keep these things under 10 minutes. Luckily, these ones all fit under the 10-minute time point that I'm trying to get. And I went ahead and did it for the skin ones also. And there's a 15-minute, 12-minute, 12-minute. So I'm not really quite getting it there that I want to. Either that means I need to break those up into two separate things, or I need to just do something about it. One thing I am doing about it, and I don't know if this is coming across as really weird, in the software that I use to record stuff, I can go in there and manipulate the sound file. So I sometimes don't say anything for a little while. I was demonstrating that. I stammer when I talk, and really what it is just I'm talking off the top of my head. So every so often I stop. I have to think about the next word I want to say. I'm sure it's endearing when I'm doing it here in live in this presentation format of a lecture. That's what I'm trying to say. But when I'm recording it, it's probably just frustrating. So I actually go in there and I cut out all of the blank spaces so that it's not wasting time just sitting there stammering. That could, however, make things a little weird because there'll be these edits in there. I try to leave a fraction of a second there so it's not just, you know, piling words up on top of words, but compared to what you're used to hearing me say when I talk in real life, it's probably unusual that it's going by really fast and that sort of thing. I'm also noticing as I do that I have certain filler words. So like, a lot of people say, and I certainly say that myself. But I also will say, now, whatever, or but, da-da-da, and all those things. I can actually cut most of those words out in the presentation, and it doesn't change the meaning of the presentation. So I'm trying to do that a little bit too. So it saves a little bit of time in the presentation. It hopefully is less frustrating listening to me talk, that sort of thing. I'm just not the sort of person that can extemporaneously sound like a rehearsed, scripted speaker. So I'm doing what I can in retrospect. Someday in the future, which will probably be several semesters down the road, I'll get these things tightened up and they'll be done better. But what you have this semester is kind of what I can do on the fly. Now, I am caught up to our present point in the course, so I have all the stuff for the bone chapter. And I'm going to work on the joints chapter next, which hopefully I'll have done tomorrow. I don't have anything going tomorrow, so I hope I can get that done. That should be a pretty short chapter to put together. It's really kind of just a transitional thing. So I'll have that up, and I should be able to get these things done in a little bit more timely fashion. I say that, and in the end I can't, but I'm trying really hard to be on top of these things. So that's what's going on there. Now, I want to finish talking about the bone stuff today. Now that I have the online content to some degree, it's already kind of there. So in the hour or so that I have here, I want to make sure I touch on some things that are important. So last time I talked about the functions of the skeletal system and the structure of bones as organs. And so what we want to deal with today is how bones grow. Now, I'm not going to go back to the presentation that I was using last time. I'll just work off of the pictures from the book directly, which are in the presentation. But this will also sort of draw me to follow the format of the book somewhat, the order that it does things in. So we're going to talk about mostly how bones grow and also how they repair themselves, which is really just a growth process itself. And I want to introduce a few terms first. The first term I want to introduce is ossification. This is a Latin word that basically means bone growth. I'm actually not positive if the book actually says the other word I want to introduce, but the Greek version of this word, so the way that you say bone growth from Greek roots, is osteogenesis. So os, O-S-S, in Latin is a root for bone. And then osteo is the root in Greek. And then in Latin, the ification ending is sort of saying the process of or something like that. It's a little harder to translate the rest of that word directly from parts of words, but it means making bones. Osteogenesis, the Greek word, is a little bit more obviously meaning that, because genesis, you probably heard that word itself, but also the root gen is the root of the word generate, those sorts of things. So it's talking about making things. So osteogenesis is making. We'll tend to use the Latin word when we're talking about the formal processes of bone growth, but just as easily we could say growth there. So this could be intramembranous growth as easily as intramembranous ossification. And when I say ossification, it always sounds like that joke about talking to a police officer when you're drunk. You know, ossification, ossifer, forget it. So there are two forms of bone growth that we want to consider, which is really how the fetal skeleton comes into existence to begin with. The first is intramembranous ossification, which I'll get to in a second. The other one is endochondral ossification. And so I want to take a second to just talk about those two terms together. So intramembranous ossification and endochondral ossification. Again, it could just as easily be intramembranous growth and endochondral growth. Now, I want to say a couple of things about each one. Intramembranous ossification means that mesenchyme directly becomes bone. And endochondral means mesenchyme becomes cartilage, which becomes bone. Now, the way I've done this under endochondral, I've put mesenchyme in parentheses because when we talk about endochondral growth, we actually don't really worry about the mesenchyme step. We just start with cartilage and see how it develops into bone. But I wanted to put mesenchyme there because remember, all connective tissues ultimately come from mesenchyme. And while there are situations where bone comes directly from mesenchyme, there are also situations where bone comes through an intermediate connective tissue, which eventually comes from mesenchyme. So the other thing to mention about these two is what bones are going to develop this way. And primarily intramembranous ossification is for bones of the skull and the clavicles. Now, if you do a little digging and you read a bit more about intramembranous ossification, you will see that there are a few other bones that fall into that group. And also that it's not 100% how, especially the clavicles, actually develop, but primarily we associate the clavicles with that type of growth. And then endochondral ossification is how all other bones develop. And I just want to make this point of except for sesamoid bones. Remember, sesamoid bones are defined because they're the calcification of some other soft tissue, usually a tendon. But so those are special case. But except for the ones that develop through intramembranous ossification, all other bones form through endochondral ossification. So, now, what's special about the skull and clavicles? Why are they set aside from all the other bones of the skeleton? Now, the real clue to being able to answer this question is it has to do with birth. So if you don't have a uterus, you might not be able to answer this question.
Different bones fuse together to make them?
Nope. I mean, we could say that about a number of different bones.
They are softer.
So they will be softer, yes. Why is that important if we consider it in terms of birth?
To ease the birth. Because that's supposed to come out first.
Well, because the head and the shoulders, and the clavicles basically establish the width of the shoulders, are the widest parts of the newborn. Okay. Once the head and shoulders pass through the birth canal, everything else is gravy. Okay. So those bones can develop in a different, like I know. The other bones can develop and be pretty calcified at the point of birth, and they're not going to be as big of a problem as passing the skull and the clavicles through the birth canal. So the skull especially, people are most familiar with how it's kind of soft at the time of birth, or it has soft spots in it. If you do an image search for this, and I don't quite know how to put in the proper search terms for it, but you can look for pictures of skulls of babies that spent too long in the birth canal. So when labor was very long and the head was in the birth canal for a long time before it finally got out, the skull ends up looking like some sort of alien creature out of, the last Indiana Jones movie. And And that's because the skull is actually soft tissue, and so when it's stuck in the birth canal for a long time, it will get elongated, it'll get squeezed out. It should be able to come back to its original shape after that. It's entirely possible, actually, to sort of force it to do that. You can have children with that issue wear a sort of a helmet kind of thing that will help form the skull into the correct shape, which at that point, oh shoot, I forget the word. I can't remember the word now, but for mammalian births, which are live births as opposed to creatures that are born in, eggs, like fish and reptiles and birds. For mammals, newborns fall into one of two different categories, and I can't remember the category that humans belong to. The other one is called precocious, so whatever the opposite of precocious is, that's what it is. So in precocious births, those are newborns that are born pretty advanced and they can start to do things immediately. Like a newborn horse will stand up and start walking around pretty much right after it's born. I'm most familiar with this concept because I used to work with ferrets in graduate school. And ferrets and cats have the same basic gestational plan, but ferrets are born 41 days after conception, and cats are born 60 some odd days after conception. So a ferret is basically born 20 days earlier than a cat, okay? Which is great when you're studying developmental processes in the brain, because you can look at a newborn ferret a lot easier than you can look at an in vitro cat. So cats are essentially precocious, and then ferrets are whatever the other word is. And I can never remember what it is. But humans fall into that group too, which is to say that we're not quite done when we come out of the oven, so to speak. Okay? The skull has not completely formed into the calcified bone. We can't walk. We can't do a lot of things. A lot of motor skills aren't even available to the newborn or to the infant until it's like 3 or 4 months old. And so as we talk about the skeletal development, the skull and clavicles are essentially soft at the time of birth, which makes it easier for the newborn to work through the birth canal. And your mother's very happy for that fact because if we were more precocious, because of the size of our brains, the head would have to be quite large when it comes to the birth canal. So the softness of the skull and the clavicles makes that process a little bit easier. Okay, so this is a figure that kind of lays out the basic steps in intramembranous ossification. If I were the art director for a book like this, I would have drawn this a little bit differently, in that I'd have one more picture before everything here to show the instant of when this starts off. So they start by showing us a small population of cells, which are the developing bone. It's what we call an ossification center. But really, we should back up a little bit further from this, because only one cell started all of this off. So let's pretend it's this cell in the center. That cell used to be a mesenchymal cell. Okay? Mesenchyme is embryonic connective tissue. And when mesenchyme becomes a different type of connective tissue, one of the cells in the mesenchyme, which we call a mesenchymal cell, just a weird pronunciation change going from mesenchyme to the adjective form of that word. One of those cells switches on certain genes and switches off other genes, so it differentiates into a different type of cell. And when that mesenchymal cell does that, it becomes an osteoblast. Okay, so it switches off certain genes and switches on other genes so that it becomes an osteoblast. And some of the genes that it switches on are genes that make products called osteoids. Okay. Osteoids are protein complexes which will help to incorporate the calcium phosphate crystals into the bone structure, into the bone matrix. So when we see the as yet unformed bone matrix, it's usually represented by this light blue color here. And then we see the dots of osteoids. That's going to end up becoming bone matrix, which is what's filling in the space in the next picture here. So one of the mesenchymal cells becomes an osteoblast and starts secreting osteoids to start developing that calcification center. Then it divides into two cells, which are both osteoblasts and both secreting osteoids. And then those two cells each divide, giving us 4, and then those 4 become 8, 8 becomes 16, et cetera, et cetera. So in this picture, they're just showing a small population of cells. All of the cells represented here would have come from that original osteoblast that started the ossification center. And the fact that this is not an even number of cells here, based on powers of 2, annoys me to no end. But really, if this is the original cell, it would have divided into 2, and then those 2 would have divided into 4, and then those 4 should give rise to 8 total. But we only have 7. Anyways, so as the bone matrix and osteoids progress to become more calcified, some cells stay behind within the bone matrix and they become osteocytes. Their job is to maintain that bone matrix for the rest of the life of the tissue. So they differentiate even further into the fully mature form of the osteocyte. But then other osteoblasts, which are the result of further division of these cells here, will end up taking up a position on the outside of the ossification center, laying down more osteoids and making more bone matrix and growing out from that center. Eventually, the bone will grow into a structure sort of like this. The ossification center is just growing randomly and cells are kind of moving off in all sorts of different directions. And that's going to end up making, at the tissue level, spongy bone tissue. Okay? So the spongy bone tissue is characterized by having these little spicules or bridges, or however you want to describe them, of bone tissue, which are formerly called trabeculae, which will have a bunch of space within them. And as the spongy bone tissue is developing, blood vessels will grow into that tissue. So there might be blood vessels within the mesenchyme around it, but they'll grow into the developing bone tissue and really invest the space within the spongy bone so that the bone tissue will be able to get its nutrients and whatnot. Eventually, the edges of the bone as it's developing will form a thin outer coating of compact bone structure, giving the bone a smooth outer surface, but the center of it will be spongy bone. And that's really the structure we see for pretty much all bones, except for long bones. But that's how intramembranous growth takes place. Outside of the developing bone, the adjacent mesenchyme is going to start to form into another type of connective tissue, which is dense irregular connective tissue, to form the fibrous periosteum layer. Okay, remember we were looking at the structure of bone last time. There was a periosteum, which had a layer of osteoblasts and a layer called the fibrous periosteum, which is dense irregular connective tissue. And that's what the mesenchyme out here is going to become. What's not drawn into these pictures is the spaces within the spongy bone here, where we do see the blood vessels, will also be filled with spongy bone. With red bone marrow. Now, this little ossification center that started everything off grows out kind of randomly and takes up this space. but it's going to grow around the rest of the mesenchyme. So actually during development, there's mesenchyme within these spaces. And that mesenchyme develops into red bone marrow to take up the space within the spongy bone, which isn't exactly depicted in this picture, but that is in fact happening. That's where the red bone marrow comes from. Other mesenchyme that the spongy bone's forming around just develops into that type of connective tissue. So that is intramembranous growth. Endochondral growth is the other form, is the other form of how the skeleton grows. We're going to consider the steps of endochondral growth in terms of a long bone, but it's happening for all of the other bones. I'll explain how it relates to the other bones in a sec. So, mesenchyme forms into cartilage, and the initial fetal skeleton is just a cartilage skeleton. Now, we think of skeletons as being made out of bone because that's what we have. And it's most common what we think of for skeletons, but really that's something that's not common across all animals. Within vertebrates, the group of animals that we belong to, most types of organisms do in fact have bony skeletons, but there are cartilaginous skeleton organisms too. The split, so to speak, or the development of the bony skeleton body plan developed within fish. So we have cartilaginous skeleton fish and we have bony skeleton fish. And from bony skeleton fish, we get land animals. And a bony skeleton is necessary for a multicellular organism to exist on the land. So amphibians, reptiles, birds, and mammals all have bony skeletons. And in fish, there are cartilaginous and there are bony fish. You're probably familiar with bony fish if you eat fish as a food, because sometimes you get a bone in the fish that you're eating. That's generally what we think of as, the regular fish-shaped fish. Tuna, salmon, whatever it is, those kinds of fish. Cartilaginous fish are sharks, rays, and a group of fish called jawless fish, which are kind of disgusting. Their sort of representative example is a lamprey, which is sort of a tube with this ugly kind of mouth thing on the end of it. I could, yes. Or you could on your own time. This is not actually a comparative anatomy course. I'm just trying to give you a little background about cartilaginous skeletons. So those are all animals that have cartilaginous skeletons. They exist in the sea, and so they're surrounded by a medium, the ocean water, that's about the same density as they are. So they don't need a bony skeleton to support their body the same way that we do, because we're surrounded by a medium, i.e. the air, which is at very different density than us, and would not be able to support us if we had a soft tissue skeleton. But in fetal development, we do have cartilaginous bones. It's sort of like the cartilage is there as a placeholder or a blank that's going to become this bone eventually. So it is hyaline cartilage as far as the specific type of tissue that makes it up. At the beginning of endochondral ossification, in the center of the bone, which is going to be the diaphysis of a long bone, it'll start to calcify and an ossification center will form there, called the primary ossification center. Now, cartilage is an avascular tissue. So there are not blood vessels in this little structure here. Now, this is very, very small. And so as it starts to calcify, the blood vessels can grow into it and form the blood support for the bone. Where the initial blood vessel grows in, which is going to basically be the center of the diaphysis. That's what we call the nutrient artery. And when the bone matrix forms around that artery, we call that the nutrient foramen, which I guess isn't technically labeled here. But they just show an artery here, but whenever we have an artery, we've got to have a vein with that too. There's also going to be a nerve going in there and probably another thing called a lymphatic vessel. We usually see all those things together, but they grow into the developing bone. So the primary ossification center starts to calcify the cartilage tissue, and eventually the diaphysis grows out so that it's just the compact bone wall with this hollow center, and the nutrient artery coming in, the nutrient vein coming out, all of that invests into that area. And it takes on its final sort of diaphyseal appearance, if you will. But that only extends up to a certain point. Okay? Then the rest of the bone is what we call the epiphysis. And the epiphysis goes through a very, very similar process to what we just saw with the diaphysis. It just happens a little bit later. And in the epiphysis, a secondary ossification center forms. Blood vessels grow into that tissue as it calcifies, and it forms our epiphysis. Now, what's different about this is, one, it's all spongy bone in the middle. Okay, it doesn't develop a medullary cavity like the diaphysis, and it doesn't completely calcify all the way out to the edge of the epiphysis. There's going to be a cartilage layer surrounding the whole thing. The cartilage that's on the outside surface of the epiphysis, some of that's going to become what we call the articular cartilage, which means the joint cartilage. Where this bone makes a joint with another bone, there's going to be cartilage in between those two bones acting as a cushion. And so some of that cartilage from the original bone precursor remains and becomes that articular cartilage. Anywhere that the bone's not going to become, or anywhere that the bone's not going to be part of a joint, so like this is the humerus, let's say this part of the head is going to fit into the shoulder joint, this part of the head's not. So it doesn't need to have a cartilage cushion on the outside because it's not interacting with another bone. So this cartilage on the side is going to eventually calcify completely, and the periosteum will be covering that area there. Then the other part that we have is the cartilage that's between the epiphysis and the diaphysis. And this is here to provide a place where the bone's going to grow longer. Okay, that's going to be the growth plate, or the epiphyseal plate right there, which we'll talk about that process in a second. So, essentially with endochondral growth, the original cartilage precursor starts to calcify, and a primary ossification center grows into the center, making the diaphysis. And then both epiphyses develop, each for their own, a secondary ossification center. And it calcifies, but leaves a little bit of cartilage on the outside, which will adapt to exactly what that bone needs to do in relation to other bones for articular cartilage or the growth plate or that sort of thing. Okay. Now, both epiphyses are going to do the same thing at approximately the same time. They just happen after the diaphysis. So we call those secondary ossification centers. For other bones, aside from the ones that go through intramembranous that we were talking about a second ago, but flat bones like the rib or the sternum, irregular bones like the vertebra, or short bones like the carpals, they're going to go through the same sort of development process, but they only have a single ossification center. So all other bones essentially develop like an epiphysis. They don't have a primary ossification center making a diaphysis because diaphyses are something that only long bones have. Okay, so for all other bones, what they do is basically the last two steps here that we see for the epiphyses. So the cartilage precursor for the bone starts to calcify, blood vessels grow into it, and the outside remains cartilage until the bone finalizes its relationship to its neighbors, keeping articular cartilage where it needs and allowing that cartilage to be fully calcified where it doesn't need a cushion on the outside. Okay. So those are the two main types of bone growth. Can't quite get that all on the same page, but intramembranous growth and endochondral growth is essentially how all of the skeleton initially forms, okay, in the fetus. Any questions about the processes? Okay. Oh, I didn't say this before, but endochondral translates directly to within cartilage. Okay. Endo, within. Chondro is the root, I can't remember if it's Greek or Latin, for cartilage. Must be Latin because, nope, scratch that, I have no idea. So endochondral means within cartilage. And that's exactly what it is. So once we have the skeleton produced during development and we have a newborn, you might not have noticed this, but newborns are a lot shorter than adults. Okay, so something has to happen after birth to make the bones grow longer. And that growth is what's represented in this picture and this picture here. I like this picture. I don't think most other books quite have something like this, but it's just showing us two femurs, in this case, of different lengths. So this would be a femur in a child, say, and this would be a femur in an adult. Okay, and it gets longer. They've also highlighted where the growth plates are. So there's a growth plate right there, there's a growth plate right there, there's a growth plate right there. So the bone sort of grows out from those places and becomes longer. And when it eventually grows to its full length, those growth plates calcify also, leaving us with a visible line of calcified bone tissue where the growth plate used to be. Now, I said I just wanted to use stuff from the book, but actually, let me go to the presentation real quick because I have a picture that I want to show you. So you can see the growth plate in an X-ray. And I explained this in the presentation, but I do want to touch on it here because I think it's important that you understand what's happening in an X-ray. So if this thing would just freaking load already. So as it's loading, I can do the first explanation of this. Of course, now it's loading. No, it's not. So X-ray imaging works on a principle very similar to just plain old photography. Now, photography these days is all digital for the most part, but film photography is what I'm talking about. In film photography, what you do is you expose a piece of film to light, and on that piece of film is an emulsion, a layer of chemicals that are sensitive to light. And so when light hits the film, it creates a chemical change that you can see once you've processed that film in a chemical bath. Now, when you're taking pictures, like on your vacation, and you're hoping to get little snapshots to put in your album or something like that, that process is actually two steps. You take a picture onto film, and then you use the film to make a print. Both of them work in the same process. It's just that we're dealing with negative images in the middle of all of this. So, and X-rays basically work. All right. It didn't want to load, so let me get it started. X-rays basically work. Imagine the screen here is the film, and the projector is sending out a stream of X-rays, okay, which could just as easily be light if we're talking about film photography. Anything that I put in the light path, and for X-rays this is a little bit more obvious, is going to block the light and it won't hit the film. So the shadow that I just made on the screen with my hand is keeping the light, or X-rays if you want to think of it that way, from hitting the film. Okay? Anywhere that light or X-rays hit their respective films, it creates a change. And so if you put something in the light path or the X-ray path and it blocks the X-rays, those X-rays will never get to the film and the film won't be exposed right there. So, oh, come on. All right, I'm tired of this. Let me just pull. Yeah, you left and I was waiting for this to load and you're back and it still hasn't loaded. I could, but I won't. Okay, so this couldn't be a bigger picture already? Well, actually, the Wikipedia picture is, oh, this will do. Okay. So we can actually see the Wikipedia version of what I'm showing you, which is what I have in the presentation, is a pretty good example of what I'm showing you. But we can see a little hint of something right there and right there representing the growth plates of the distal end of the tibia and the fibula. So this is the distal epiphysis, and this is the diaphysis. Distal epiphysis, diaphysis. We can see a line separating the two there. Now, I'm not positive about what age this picture is actually from. Shoot, not what I wanted. Oh, there we go. This is the one from the Wikipedia page. So we can see even more definitively that there's a line right there, a line right there. You can, I think you can really get the sense that that's a real gap. There's a space between the epiphysis and the diaphysis in the fibula there. The tibia being a thicker bone, you can't see that gap quite as easily, but it is there. The reason we see that gap is because of how X-rays work. Now, remember I just did the explanation. I put my hand in front of the light path. Now the background here is black, so there's not a lot of light to block, but the shadow of my hand is keeping light from hitting the screen. And when you do an X-ray, you put somebody in front of the X-ray source and you shoot the X-rays through them, and then whatever hits the film is whatever passes through their body. The thing that you can see most easily on an X-ray is a bone. Okay? When we cast a shadow onto an X-ray, the shadow is white, and what's black is what gets exposed. That's what I meant when I said something about negative images. This process of exposing light to a photographic film or X-rays to an X-ray film is a negative process, because what happens to the chemicals in the emulsion when you expose them to light is that they get dark. Okay. Now, I'm actually not sure about X-rays, but in film photography, the emulsion is made up of a silver compound. And that silver compound, when it's exposed to light, becomes a black pigment. Okay. how much light it's exposed to over the emulsion will establish how dark the pigment gets. So, and that's just for black and white photography. For color photography, it's a little bit more involved. So the colors are represented. But if you look at the negative image of a color film, then all of the colors are backwards. Red is green, blue is yellow, green is magenta. Something got messed up in saying that, but all of the colors are the opposites. Here we're just talking about black and white, which is all you can get from an X-ray image. So what the X-rays pass through makes black on the film, and what they don't pass through makes white. So obviously the densest thing that an X-ray is going to show you is the bone tissue. Why does bone tissue block X-rays so well? Why is bone tissue dense? Right, it's calcified. It's got a crystal structure of calcium phosphate in it. Okay. You are probably kind of familiar with what like a salt crystal looks like from table salt. It's kind of a cubic structure. Okay. If you could look at them under the microscope, the smallest sodium chloride crystals you can see are cubes. That's the way that that salt arranges itself. I'm not entirely sure, but calcium phosphate salts, they make a very complex crystal structure. I don't know what shape the crystal structure actually is, but you can ground salt down pretty easily. Okay? It's not that strong of a crystal structure. But calcium phosphate crystals are very durable, and we have proof of that down the hall. We have, aside from the plastic bones, of course, we have a bunch of bones that are just collections of calcium phosphate crystals that have long survived the rest of the body that they came out of. Okay? And it takes a lot to start breaking down the crystal structure there. So when you were working with the bones, Tuesday, right? Yeah. When you were working with the bones, you might have noticed some of the bones you could see exposed spongy bone, especially at the ends. That's because people over the 30 some odd years that we've have had those bones, just in handling them, the bone structure's broken down a little bit so we can see inside, or somebody's dropped it or something like that. But for the most part, bones are still pretty much intact because that calcium phosphate crystal structure is so strong. And being very strong, it's very dense, and it blocks X-rays very easily. Now, we can see a hint of the outline of this kid's ankle. Okay, now, this is a kid. We know it's a kid because there's a growth plate there. If it was a grown person, there wouldn't be a growth plate. But this sort of grayish color that we can see outlining the full ankle, that's the soft tissue that we see beyond the bone. It's not as easy to see. Okay, it's just a shade of gray between the white that we see of the densest parts of the bone and the black that we see of the air that the X-rays are just passing through. But why can we see soft tissues? What makes soft tissue dense? Any idea what the densest thing in any tissue in your body is? If I were showing you a picture of the torso, an X-ray of the torso, it would probably be pretty obvious, because what you can see easiest of soft tissues there is the heart, the liver, and the spleen. What do those three organs have a lot of? Blood. Okay. So there's something in blood that's very dense. What does blood have that's very dense?
Iron.
Iron, right. Iron ions bind up the oxygen. Iron's a heavy metal. Okay. Carbon, oxygen, nitrogen, sulfur, all the things that are making up most organic molecules are relatively small atoms compared to something like iron. Iron has a huge nucleus, and so it blocks a lot more X-rays. And it's just sort of all throughout that soft tissue. So you can see soft tissues to some degree depending on how much blood is in the tissue. So what do you think is going to happen to an avascular tissue like cartilage?
You can't see it.
Right. There's nothing there that really stops the X-rays that well. So especially right here, you can see no difference between the growth plate here at the edge of the fibula and the other soft tissues outside of the bone structure. So there's nothing there to see. Now we do see a little gray because there are other soft tissues in the path of the X-ray that's passing through there. It's not going to give us a complete void just because there's cartilage there. But where there is cartilage, it's going to block X-rays much more poorly than most everything else. Okay? And so especially when we see the cartilage, the growth plate next to the very dense bone tissue of the diaphysis, it's very easy to see that. I'm just trying to pull up an adult X-ray. I mean, adult. Okay, ignore the fact that there's a break here, but now we don't see a gap in between the epiphysis and the diaphysis of the fibula here in the before picture, and we don't really see one between the epiphysis and diaphysis of the femur, except where this little bit of the not femur. Tibia. This little bit of the tibia, the medial malleolus is broken off. So obviously that's the injury that this is all about. You can kind of imagine a line going right about there, which is what's left of the growth plate. And when the growth plate finally finishes calcifying, we can see some calcium, some denser calcium structure there where it was. Okay, so that's to show you what it looks like through the X-ray. Let me pull up this picture that shows how this takes place. So, at the growth plate, we have cartilage tissue that's going to eventually become bone tissue. And the cartilage has to go through a few different changes. Now, as cartilage is becoming bone, some blood vessels will grow into it. So I told you that cartilage is avascular. The fact that we do see some blood vessels up here isn't inconsistent with the way that it's going to eventually be. But we have some cartilage that's called the reserve zone. I've seen other sources called the resting zone, which is basically cartilage that's not doing anything yet. At the edge of that resting or reserve zone, there will be chondrocytes which start to proliferate. And when they proliferate or divide really fast, they basically stack cells up on top of each other. So one cell divided into two, and then those two divided into four, and those four, and it just keeps growing out that area. They're just going through cell division, mitosis, very rapidly. Now they're doing it so quickly that the cells don't really have time to grow in between divisions. So older cells that have finished going through this proliferation division will take up the next zone where they start to mature in hypertrophy, which basically means grow bigger. So this is called the reserve zone. This is called the proliferative zone. This is not called the something or another zone, but some sources will probably call it the hypertrophic zone, just meaning that it's where the cells grow bigger. And then those cells that were growing and laying down all this new cartilage tissue, those cells die. And the tissue becomes calcified and it becomes actual bone. So really in the growth plate, what's happening is the cartilage is growing thicker and thicker. And then the cartilage calcifies. You can say that what's happening at the growth plate, this growth of the bones into longer bones is really just a form of endochondral growth. It's just the cartilage is what's growing in there. So if we go back to this picture here, real quick. Oh, not this picture. Where'd it go? Oh, well, I must have closed that picture. But this picture here, the two femurs, the picture doesn't represent this, but what's actually happening at the growth plate is that the cartilage is growing and, well, I should say, the cartilage grows and sort of pushes the epiphysis out, and then the older cartilage in the growth plate calcifies behind it. And so this shorter bone gets longer as the growth plates kind of push the epiphyses out and the diaphysis grows longer. Now, the epiphysis is obviously broader than the diaphysis. So in this process, while it's growing, the growth plate is growing out, it's also remodeling and forming into the final shape of the bone, which is going to be the diaphysis. So that's how bones get longer postnatally. Also postnatally, and this really is a lifelong kind of growth, bones will grow in diameter. Now in the book, they talk about growing in diameter and bone remodeling as if they're really two different things, but they're not. It's the same process. It's just a matter of when it's taking place. So in the paragraph under how bones grow in diameter, the last word, which is boldface, is modeling. And then they go right into bone remodeling. And it's really the same process. Unfortunately, in the book, they don't give you an appropriate name or description of what's happening there. So in the presentation, which I'm sure never fully loaded, I closed it anyways. I embedded this video, and I have it actually in the video content section on Blackboard as well. Oh man, where is it? There we go. This is a process called appositional growth. And this little video, which I don't have the sound on, shows it happening. So the outside edge of the bone starts to grow a little thicker, and the bone will surround blood vessels that are on the outside of the bone, and they end up being incorporated into the center of a cylindrical structure. There we go. Which then grows inward to completely surround the blood vessel. Go ahead, you can do it. There we go. And what that forms is a new osteon. Okay. So the outside edge of bone is compact bone tissue. And, oh, didn't quite get there. Okay. The outside edge of every bone is compact bone tissue. And so the outside edge can grow a little thicker. There are blood vessels on the outside of the bones. And so the bone just sort of grows around those and forms a new osteon, with that blood vessel that it grew around being the blood vessel of the central canal. And it can keep doing that. That's appositional growth. Appositional means essentially on the outside or on the edge. It's very close to the word oppositional. Okay, when you're opposed to something with an O, you're against it sort of figuratively, I guess you could say. You're opposed to the school raising student fees. Okay? But to be opposed to something with an A means that you're physically against it. So I am opposed to the whiteboard as I lean against it. So appositional growth is referring to growth right at the edge of the bone. Now, in the modeling and remodeling things that the book mentions, and even introducing the idea of appositional growth here, what's left out is the balance of that, which is when you add bone matrix somewhere, you have to take away bone matrix somewhere else. If it all just kept growing in diameter and remodeling, you'd eventually get big, massive, compact bone structures that would be too heavy to do anything with. So there has to be a balance between adding bone matrix and taking bone matrix away. And that is handled in, where is it? The idea of calcium homeostasis. So there's a section here in the book on that, and I covered in the presentations, which is how we balance calcium levels in the blood. So this is a straightforward homeostatic mechanism. We should have a normal level of calcium in our blood, which is in the neighborhood of 10 milligrams per deciliter, okay, which is a standard measurement of concentration of something in the blood. If your blood calcium levels go up, then part of the thyroid gland recognizes that change, and it releases a hormone called calcitonin. Hopefully you can see calcitonin has, as its root, the same root that gives us calcium. Calcitonin targets osteoclasts, which are the cells that break down bone matrix, and inhibits their activity. And by doing that, then the bone's going to preferentially add more bone matrix and more calcium to the bone. Okay. When that happens, also the kidneys decrease reabsorption of calcium, which means that you pass more calcium in your urine. Okay. Calcitonin doesn't actually do that. The absence of what goes on in the bottom half of this picture is really why you're passing more calcium in your urine. But either of those things end up decreasing calcium levels in the blood, either by storing it in your bone or getting rid of it in your urine, and you get back to your normal calcium levels. If your calcium levels go down, then the parathyroid glands sense that change, and they release their hormone called PTH. Now, PTH stands for parathyroid hormone, but please just refer to it by its initials, PTH. It's going to keep you from misspelling a word, and I see that a lot. So in any question that is looking for a reference to this, it will take parathyroid hormone or PTH, but I would strongly suggest just use the abbreviation. It's a lot harder to misspell that. PTH also targets the osteoclasts and makes them more active, so they release more calcium from the bone matrix. And then PTH targets the kidneys and causes calcium reabsorption or retention in the blood, so you don't lose it into your urine. So really, up here where it says you decrease calcium reabsorption in the kidneys, it's really because PTH levels are low, and so the kidneys aren't being told to retain calcium, so you get rid of it in your urine. And then PTH signaling the kidneys to reabsorb calcium will also tell the kidneys to make another hormone that tells the intestines to absorb more calcium out of your food. Okay. All of which will raise blood calcium levels, either by releasing calcium from the bones, retaining calcium instead of passing it in your urine, or getting more calcium out of the food you eat. All of those will raise blood calcium levels. Obviously, if you don't have any food in your intestines, then this last thing is not going to do a lot of good. But if you are digesting food, then it'll help keep those levels up. Now, in the presentation, I talk about this in a little bit more detail. I talk a little bit about exactly where on the thyroid gland calcitonin comes from and those sorts of things. Also, not in the presentation, but also I want to mention both of these hormones, calcitonin and PTH, target osteoclasts. What's the other type of bone cell that's making the bone matrix, which we've talked about plenty today? So the osteoclast is the osteoclast. Right? So in keeping growth and breakdown in balance, basically those two cells are kind of working at the same levels. You're building as much bone matrix with osteoblasts as you're taking bone matrix apart with osteoclasts. So those should stay in equilibrium. But when your equilibrium's off, because your calcium levels are low, the way that you actually do anything about it is these two hormones affect the osteoclasts. So calcitonin inhibits osteoclasts so that there's, relatively speaking, more osteoblast activity. And PTH stimulates osteoclasts, making them more active than osteoblasts. So decreased osteoclast activity means that relatively you're adding more calcium to bone matrix. Increased osteoclast activity will remove more calcium from the bone. So they're both actually acting on the same type of cell, which is always supposed to be in balance with the osteoblasts. And when your blood calcium levels are out of balance, then you want to force those two cells out of balance. And both of them work on the osteoclast. I actually don't know any cosmic reason for why they both work on that, but it probably makes for more efficient control of the homeostatic mechanism or something like that. But I'm not an osteologist, I guess that would be. So I don't know the specifics of that. So, the other thing in the book, there we go, which I'm not going to talk about, it's covered in the presentations, is how bones heal from fractures. Any book like this is going to list the different types of fractures. It's a very easy bit of information, really just definition kind of things. And if you're interested in it, feel free to incorporate this information. But it might be present in a multiple choice question from part 1 or 2, more likely part 1 than 2 from the chapter. But definitely there will be no questions in part 3 or 4 for the bone chapter asking you anything about the types of fractures, because I don't think that that's necessarily that crucial to know. Okay. And then I also describe how bones repair themselves. So actually back when we were looking at tissue, I talked about how epithelial and connective tissues heal in the context of a cut through your skin, but in general how those tissues heal. Here we see the same sorts of things happening, but it's specifically bone tissue that's healing. And there's some special aspects of it because of how bones have to do their job, which is to be very strong and dense. So I cover that stuff in the presentation thing too. So, any questions? All right, so if you don't have any questions, I'm done for the day. And let's see, Monday, we're doing the practical. That's all we're doing on Monday. You might very well be done by 11 or so. Don't count on it. You will have until 12 if you need it, but when you're done, you'll be able to leave from lab. And then next week, we'll be dealing with joints and stuff.
What are the this is how much?